Welcome back to the Deep Dive. We're the place you come to get past the headlines, sift through the really interesting research, the complex questions, and, well, hopefully leave you feeling genuinely well-informed. Today, we're heading somewhere pretty extraordinary, right into the heart of modern medicine, the operating theater. We're exploring a world where, incredible precision isn't just like a nice-to-have, it's a daily reality. Saves lives. Think about it. Not that long ago, major surgery meant big incisions, long recoveries, lots of discomfort. Now, fast forward to today, and many complex procedures happen through tiny keyholes. You barely see them. That's minimally invasive surgery, MIS. It's revolutionary. Less trauma, faster healing, shorter hospital stays, just amazing ingenuity. And right at the core of these really delicate operations, you find this versatile tool, kind of an unsung hero, really. Now, the catheter. It's not just a tube, right? It's this flexible instrument navigating the body, crucial for heart repairs, pancreas procedures, cervix, all sorts of things. It's like an extension of the surgeon's own hands, almost. Okay, let's unpack this a bit.
MIS is fantastic, no doubt, but it brings its own challenges. Surgeons get these amazing camera views, high def, inside the body. But what's often missing, what gets lost in these super high-tech visual procedures?
Well, it's that fundamental sense of touch, that intuitive feel.
Exactly, that natural feel, the resistance of tissue, the texture that guides a surgeon's hands in traditional open surgery.
When you're working remotely through tiny ports with long instruments, that direct tactile feedback is largely gone. You're relying almost entirely on what you see on the screen.
And that creates risk, right? Makes things harder.
Absolutely. And you've hit the nail on the head there. That lost sense of touch, it isn't just like a minor inconvenience, it's a significant deficit. In MIS, visual cues are vital, obviously, for knowing where you are, but there's this critical need, an urgent need, for real-time force feedback.
Okay, so not just where, but how hard you're pushing.
Precisely. How much pressure are you applying? What kind of resistance is the tissue giving back? Imagine trying to thread a needle maybe, but you could actually feel the fabric through the needle tip.
Yeah.
Feel its thickness, how much force it takes.
Yeah, okay, I get that.
That's the kind of tactile input we're aiming for here. And it's why this research we're diving into today is so groundbreaking. It's from the Indian Institute of Science. Their team has developed this really innovative solution. It's a MEMS-based force sensor built right into the catheter tip, and it's combined with a vibro-haptic feedback system.
Vibro-haptic, so vibrations the surgeon can feel.
Exactly. The paper basically promises to give surgeons back that missing sense of touch.
Right.
Which could, fundamentally change how these delicate procedures are done and how safely.
Wow. Okay. And the team behind this?
Yeah, the authors are VSN, Sitaram Gupta V, Tushar Sakorikar, and Hardik J. Pandya. It's really cutting-edge work coming out of their lab at ISC. Shows the kind of innovation happening there.
Fantastic.
Yeah.
All right, so let's really get into why. Why is this force feedback, this sense of touch, so incredibly critical in MIS? We know the benefits: tiny incisions, less post-op pain, faster recovery, shorter hospital stays, all huge wins.
Huge wins, definitely. But as you said, those advantages come with this trade-off, the loss of direct feel. And that's where the need for force feedback becomes so apparent. Its role is it's crucial. Can't really overstate it, especially for patient safety and, making sure the treatment actually works.
So what are the main reasons? Preventing damage, I imagine.
That's number one, yeah. Think about navigating a catheter through, say, fragile blood vessels or near delicate organs. If you misjudge the force, even slightly during insertion or manipulation, you could cause serious damage, vessel tears, even perforations.
Oof, yeah.
With real-time force feedback, the surgeon gets an immediate, tangible warning, like a vibration telling them, whoa, too much pressure here, allows them to back off, adjust, navigate much more safely.
Okay, that makes perfect sense.
What else? The second big thing, and this is maybe even more key for the success of the procedure, is it provides a kind of sense of palpation.
Palpation, like feeling the tissue.
Exactly. In open surgery, a surgeon can physically feel for lumps, bumps, abnormalities, differentiate tissue types just by touch. That's often lost in MIS. But with force feedback, they get this sort of remote touch. They can subtly feel the tissue at the tip, even from outside the body.
So they can tell what they're touching, not just see it.
Right. It helps identify targets, tell the difference between, say, healthy tissue and maybe diseased tissue, which might feel stiffer, or ensure they're making good contact for delivering therapy. It's incredibly valuable information.
It sounds like it. And you mentioned the balance of force being critical.
Oh, absolutely. And this is where it gets really fascinating and a big driver for this specific research. Take cardiac ablation for atrial fibrillation. That's a common procedure.
For irregular heartbeats.
Yeah. They use a catheter to create tiny scars, lesions inside the heart to block the faulty electrical signals. The force they apply is it's on a knife's edge. Well, apply too little force. The research specifically mentions less than zero point 0.1 newtons, which is tiny, and the ablation might not take. The scar isn't effective enough.
Meaning the arrhythmia comes back.
High chance of recurrence, exactly. The procedure fails, patient needs it again, or just keeps having symptoms. Not good.
Okay. And too much force.
Even more dangerous.
Huh.
The paper points out that forces over 0.3 newtons, and specifically over 0.35 newtons in their benchtop tests, risk serious complications. In experiments they did on pig hearts, in vivo forces above 0.77 newtons actually perforated the heart tissue.
Wow. Punched right through.
Yeah, catastrophic. And even before you get to perforation, too much force can cause the tissue to kind of fold over the catheter tip, which prevents the energy delivery, makes the ablation ineffective, and increases the risk of damage.
Well, there's a sweet spot.
A very narrow one. The optimal range for a good lesion and low recurrence seems to be between 0.2 and 0.3 newtons.
That's incredibly precise. Like the weight of a couple of paper clips making all the difference.
Pretty much. And that really hammers home why accurate real-time force feedback isn't just nice to have. It's absolutely essential. It lets the surgeon hit that perfect tiny window of force every time for safety and for success.
It's astonishing.
Yeah.
And engineers have tried to solve this before, right? There were other sensors.
Oh, yes. People have definitely recognized this problem for a while. They've explored things like strain gauge sensors, fiber optic sensors, capacitive sensors, trying to integrate them into catheters.
But they had drawbacks.
Yeah. They all kind of hit limitations. Some were too bulky to fit easily. Others were too fragile for the tough environment inside the body. Signal interference could be an issue. Or just the cost and complexity of making them small enough.
So a truly good solution was hard to find.
Exactly. Which is why this MEMS approach from the IS team is so exciting. It offers a new path.
MEMS, Micro-Electro-Mechanical Systems. We hear that term a lot. What makes it such a good fit here?
It really addresses the specific shortcoming of those older approaches. MEMS technology lets us build incredibly tiny devices. We're talking components on the scale of micrometers, a millionth of a meter.
Smaller than a human hair.
Way smaller for some features. They're built using microfabrication techniques, similar to making computer chips. And this miniaturization is advantage number one. Catheters are tiny. Any sensor has to fit inside that tiny tip, maybe just a few millimeters wide, without messing up its function or how it moves. MEMS makes that possible. You just couldn't get a sensor this small otherwise.
Okay, miniaturization is key. What else?
High sensitivity. Detecting those tiny force differences, 0.1, 0.2, 0.3 newtons, that requires a sensor that's incredibly responsive. MEMS devices are great at converting really small physical deflections into clear electrical signals, essential for that nuanced control.
Right, you need to pick up those subtle changes.
And thirdly, MEMS allows for more flexibility in design, more degrees of freedom. Catheters don't just push straight, they twist, turn, apply force at angles. MEMS sensors can be designed to detect these multi-directional forces, giving the surgeon a much fuller picture of what's happening at the tip.
Okay, now this is where it gets really interesting, I think. The actual sensor itself, this MEMS device. Can you paint a picture of what it actually looks like? How small are we talking?
Right, let's zoom in. Imagine these tiny, intricate structures built on silicon. The core of the sensor is a ring shape, and extending out from it are 4 identical bridges, positioned orthogonally like at north, south, east, west.
Okay, 4 little bridges.
And these bridges are seriously small. Each one is 500 micrometers long, that's half a millimeter, 200 micrometers wide, and only 35 micrometers thick.
Thinner than a hair, then.
Definitely. Significantly thinner. These bridges connect an inner ring to an outer ring. The outer ring has a diameter of 3.5 millimeters, which matches standard catheter tips. The inner ring is smaller, 1.2 millimeters across, designed for easy integration with the rest of the tip assembly.
So it's designed to fit perfectly.
Exactly. And the real clever part, structurally, is a rectangular cavity, like a tiny cutout, right where each bridge meets the rings. This cavity creates 2 distinct hinges on each bridge.
Hinges, like tiny pivot points.
Precisely. These hinges are where the mechanical stress from any applied force gets concentrated. They're the key points for detecting the force.
So the force bends these tiny hinges.
Yeah.
How does that turn into a signal? You mentioned piezoresistive elements.
Yes. That's the magic ingredient. On each corner of these bridges, near the hinges, they integrate 2 P-type piezoresistive sensing elements.
Detector.
It refers to the type of semiconductor doping. And they're very specifically oriented in the silicon crystal structure, the 110 direction, to maximize their sensitivity to stress. So 8 sensing elements in total for the whole sensor.
Okay, 8 tiny sensors on these bridges.
And piezoresistors have this neat property. Their electrical resistance changes when you stretch or compress them. So when force deforms the bridges, it stresses these elements, changes their resistance.
And bingo. Mechanical force becomes an electrical signal.
You got it. A measurable electrical signal.
But it's smarter than just detecting any force, right? It can tell the difference between pushing straight on and pushing at an angle.
Exactly. That's critical. If the force is purely normal straight down, all 4 bridges deform pretty much equally. The resistance changes in all 8 elements will be similar.
Okay, nice and uniform.
But if the force is angular, say, the tip is pushing sideways or twisting it creates an uneven load on the bridges. Some might bend more, some less. Some might experience more shear stress.
So the pattern of resistance changes is different.
Precisely. The differences in how the bridges deform, the disparity in the signals from the different piezoresistors, that tells the system the force isn't normal. It reveals the orientation, the angle of the force. Invaluable for navigation.
That is clever. And what about temperature? Does that affect things? Operating rooms can fluctuate.
Good point. Temperature changes can affect resistance, so they built in compensation. There are 8 additional fixed piezoresistors placed on the outer ring, away from the main stress points. These work together with the sensing elements in what's called a resistive divider configuration. It basically allows the system to electronically cancel out resistance changes caused just by temperature shifts.
So the signal you get is purely from the mechanical force.
That's the goal, ensures accuracy. And all of this, the exact size of those cavities, 70 by 50 by 35 microns, the piezoresistors themselves, 35 by 10 microns, wasn't just guesswork. They used sophisticated COMSOL simulation software to model and optimize everything. Iterative design to get the best sensitivity, the best performance. Every tiny detail matters.
It's genuinely mind-boggling. The precision needed for something that small, performing such a critical function. Thinner than hair, feeling forces lighter than a feather, inside a beating heart. It really underscores how crucial this detailed engineering is for patient safety.
It really does. And that precision thinking carries right over into the next challenge. How do you take this incredibly sensitive, tiny MEMS sensor and integrate it reliably into a functional catheter tip? It's not just about sticking it on there. You need a custom design that ensures the force gets transferred accurately to the sensor without damaging it or hindering the catheter.
So another piece of clever engineering needed.
Definitely. The custom tip they designed has 2 main parts. The electrode tip itself, that's the bit that actually touches the tissue, and a specialized component called the force transfer structure, or FTS.
Force transfer structure. Okay, its job is in the name.
Pretty much. And the material they chose for the FTS is really critical. They went with polyoxymethylene, or POM. You might know it as Delrin or acetyl.
Why POM? What makes it suitable?
Several key reasons. First, it's very stiff. Tensile modulus between 2 and 3 gigapascals. That stiffness is vital because you want the force to be transferred through it to the sensor, not absorbed or dampened by the FTS itself.
Right, you don't want it acting like a cushion.
Exactly. Second, POM has excellent dimensional stability. It holds its shape really well under stress, doesn't deform easily. That maintains the precise alignment needed between the FTS and the sensor bridges.
And it must be safe for medical use.
Absolutely crucial. Third reason, POM is biocompatible. Safe for use inside the body, doesn't cause adverse reactions. So, stiffness, stability, biocompatibility, the perfect combination to relay that force accurately and safely.
Okay, so how do these pieces fit together? The electrode tip, the FTS, the sensor.
It's quite intricate. The electrode tip is customized to fasten securely onto the FTS. Looks like they used very fine M2 threads. There's also a tiny 1 millimeter hole drilled for a stainless steel lumen, which likely carries wires or other necessary elements through the catheter.
So it's all tightly assembled.
Very tightly. And the FTS itself is designed with incredible precision where it meets the sensor. It has this ring-shaped base just 500 microns high and 200 microns wide.
Tiny again?
Yep. And this base aligns perfectly over the center of the sensor's 4 bridges. So when you apply that normal straight-on force to the electrode tip,
It pushes evenly on all 4 bridges via the FTS.
exactly. Equal deformation, clear signal. They also mentioned something called preloading the bridges.
Preloading.
Yeah, basically ensuring there's always a small amount of initial contact force between the FTS and the sensor, maybe just from the weight of the tip itself. This avoids any initial dead zone or offset in the readings and accounts for any slight baseline drift. Make sure the readings are accurate right from the start of applying surgical force.
Makes sense. So what happens with that angular force again mechanically?
When there's an angular force, or a twist, the force isn't evenly distributed by the FTS onto the bridges. Depending on where the force hits the tip, some bridges might get more normal force, while others experience more of what they call translated shear forces.
Shear forces. Sideways stress.
Kind of. It creates higher stress on one side of a bridge's hinge compared to the other. And that difference in stress leads to different changes in the psoas resistors on that same bridge.
Ah, so the pattern of stress within a single bridge changes too.
Exactly. That differential stress, combined with the unevenness across all the bridges, is how the sensor distinguishes angular from normal force. It's really reading the subtle mechanics. They even had to carefully choose the diameter of that internal stainless steel pipe to allow the tip to twist slightly without the pipe touching the sensor's inner ring, which would mess up the readings.
Wow. Every single part has to work together perfectly.
So what this all means for you listening is that the physical construction, the materials, the mechanics, they're just as important as the fancy sensor chip itself. It's a whole miniature system designed to capture and transfer these tiny forces accurately. It really makes the catheter tip feel like a sensitive extension of the surgeon's own hand. Okay, so we've got this amazing sensor detecting force with incredible detail. But like we said, just knowing the force isn't enough. The surgeon needs to feel it. How do we get that electrical signal from the sensor tip back to the surgeon's hand as a sensation they can actually use? This is where the vibrohaptics come in, right? Exactly, because right now, surgeons might see a force number on a screen, maybe a little graph. And that's useful data, sure.
But it's not intuitive.
Not really. It adds cognitive load. You have to consciously look at the number, interpret it, then translate that back into action. It lacks that immediate gut-level feel that's so important for dexterity and decision-making.
You want it to feel natural.
Precisely. And that's where haptic feedback, the sense of touch and pressure, is such a potential game changer for MIS. We're translating that abstract data, the resistance changes, into a tangible feeling. And specifically, vibrotactile feedback using vibrations has some key advantages for this application.
Like what?
Well, first, it's a relatively easy platform to implement. You can integrate vibration motors into handles without a massive redesign. Second, and this is important, it's highly resistant to background noise.
Yeah. Operating rooms aren't exactly quiet libraries.
Definitely not. Alarms, monitors, people talking, visual cues can be missed, auditory cues drowned out. But a direct vibration, that cuts through.
And they're small, presumably.
Yes, third advantage, small form factor. Just like the sensor, the vibration motors need to be tiny to fit into an ergonomic handle without making it bulky or awkward.
So let's trace the signal path. Sensor at the tip detects force. Then what?
Okay, imagine the flow. Sensor generates raw data. That goes into a data acquisition system, a DAQ. The DAQ digitizes it. Then it goes to a microcontroller, the system's brain, for processing. The microcontroller analyzes the force data, decides what kind of feedback is needed, and sends commands to a dedicated haptic driver chip.
And the driver controls the motors.
Exactly. The haptic driver powers tiny vibration motors called ERM motors, which are housed inside the handle the surgeon holds. So force at the tip causes a specific vibration pattern in the handle, a closed loop.
Let's break down those components a bit more. The microcontroller.
Yeah, the brain here is a PSOF 5LP microcontroller. It's pretty capable. It handles processing the sensor data. It actually has these built-in current generators, IDACs, which are perfect for converting the resistance changes from the piezo resistors into voltage signals accurately. It also has a programmable gain amplifier, a PGA, to boost weak signals from very light forces, and high-resolution analog to digital converters, ADCs, to turn those voltages into digital numbers the processor can understand.
Okay. And the DAQ system, what's special there?
The DAQ uses a 16-bit delta sigma ADC. That's a type known for high accuracy, especially with slower changing signals like force. It samples really fast, 10,000 times per second. And crucially, it uses direct memory access DMA. This means data can flow directly from the ADC to memory without constantly interrupting the main processor. Makes the whole process much more efficient, keeps latency down.
Latency, the delay between sensing and feeling, how much is there?
They measured the total system latency at around half a second, 0.5 seconds.
Is that fast enough for surgery? Half a second sounds like, well, a bit of a delay.
It's a fair question. But for procedures like cardiac ablation, the typical time the catheter tip is held in contact with the tissue to create a lesion is actually quite a bit longer, usually more than 5 seconds. So in that context, a half-second delay is considered clinically acceptable. It doesn't really hinder the surgeon's ability to react appropriately or affect the outcome.
Okay, context matters. And the motors themselves, ERMs.
ERM stands for eccentric rotating mass. Think of a tiny DC motor, like the kind that makes your phone vibrate. It has a small weight attached off-center to its spinning shaft.
So when it spins, it wobbles.
Exactly. That imbalance creates the vibration. They're small, coin-shaped usually, and to control them precisely, they use that specialized haptic driver chip, the TI-DRV2605L. This driver is important because it handles starting and stopping the motors quickly and consistently. It ensures the vibrations feel crisp and distinct. Plus, it has this library of over 100 pre-programmed haptic effects built in.
100 different vibration patterns.
Yeah, quite a range. Different buzzes, clicks, pulses.
Okay, now here's where it gets really interesting for me. How do they make that feeling actually mean something useful to the surgeon? 100 patterns sounds like it could get confusing.
That's a very smart point. They didn't just throw all 100 effects at the surgeon. They carefully selected 15 specific, predefined haptic waveforms from that library. Each one corresponds to a particular qualitative force level or type.
15 is more manageable, but still.
But here's the really clever bit. They used 2 separate ERM motors in the handle, not just one.
2 motors. Why?
Motor 1 is primarily dedicated to signaling normal force that's straight-on pressure. Its vibration might get stronger or change pattern as the normal force increases through those low, medium, high ranges we talked about. Motor 2, however, kicks in specifically for forces other than normal. So if the sensor detects significant angular force or shear force or twisting, Motor 2 activates, perhaps with a different kind of vibration pattern.
So it separates the signals. How hard from how?
Exactly. It distributes the complexity. Instead of trying to interpret one motor doing everything, the surgeon gets 2 distinct channels of tactile information. Makes it much easier and more intuitive to understand what's happening at the tip. Is it straight pressure, or is something else going on?
That is genuinely smart design. Simple but effective. And where are these motors housed?
In a custom-designed ergonomic haptic handle, it's not just a standard handle. They 3D printed it using SLA, stereolithography. That's a high-resolution printing method, lets you create really precise, complex shapes.
So it fits the hand well and holds everything securely.
Right. Comfort and usability are key for long procedures. And they paid attention to isolating the vibrations. The ERM motors sit in special enclosures on the handle surface. These enclosures have slots to help localize the vibration, make it feel distinct. And crucially, the enclosures themselves are mounted using screws, rubber grommets, and springs.
Vibration isolation.
Yep. It stops the vibration from just spreading vaguely through the whole handle. It keeps the feedback crisp, localized right under the surgeon's fingers, making it unambiguous. Direct, actionable information.
The beauty of it all is taking those invisible electrical signals from the tip and turning them into something the surgeon can actually feel. A tangible, understandable sensation. It's like giving the catheter its own language to speak directly to the surgeon's hand.
It really is. But, while the sensor and the haptics are the headline acts, there's this other critical piece of the puzzle, often overlooked but absolutely vital for MEMS devices like this. Packaging.
Packaging, like putting it in a box.
Well, a bit more complex than that. This raises a really important question the researchers had to tackle. How do you protect this incredibly tiny, delicate sensor? How do you make reliable electrical connections out of it? And how do you fit all that into the tight confines of a catheter while making sure everything is biocompatible, sterilizable, and robust enough for surgery?
Okay, yeah, sounds like a nightmare.
It's honestly one of the biggest challenges in MEMS, often harder and more expensive than making the chip itself. You need mechanical support, reliable electrical links, protection from body fluids, temperature changes, physical stress, all at that micro scale. It demands really novel solutions.
So what was their solution here? How did they package this sensor?
They developed a pretty ingenious multi-part approach. First, the fragile MEMS sensor chip itself is carefully bonded onto a small, custom-made circular printed circuit board, a PCB. They use a non-conductive epoxy for this. This little PCB is only 4.5 millimeters across and has 16 gold pads on each side for making connections. Then, they use wire bonding incredibly thin aluminum wires, just 75 microns thick, about a human hair's width, to connect the sensor's contact points to these pads on the PCB.
So that gets the signal from the tiny sensor onto a slightly more manageable board.
Exactly. Step 1. Then comes the assembly to protect it and connect it further. There's an internally threaded acrylic cap, about 6 millimeters wide, 7 millimeters long. This goes over the sensor and PCB like a protective shell. This cap then screws into another custom part, a threaded, hollow acrylic stud. But the real stars for making the electrical connection out through the catheter are these things called spring-loaded pogo pins.
Pogo pins. That kind of charging dock?
Similar idea, but miniature. They're tiny spring-loaded plungers. They provide a reliable electrical contact even if there's slight movement, vibration, or misalignment. Much more robust for something flexible like a catheter than trying to solder tiny wires all the way through.
Ah, clever. How many do they use?
16 of them, connecting to those pads on the little PCB. These pins press against corresponding pads further down the line, ensuring a solid electrical path from the sensor through the catheter body to the external electronics. They even used custom alignment PCBs with little holes to keep the pogo pins perfectly straight and ensure good contact. It's a really well thought out mechanical and electrical solution.
Okay, so now they have this fully assembled packaged catheter. Time to test it rigorously.
Absolutely. You have to characterize its performance precisely. They took the finished catheter, sheathed it in a standard silicone feeding tube 12 French size to mimic how it would be used clinically. Then they put it in this very precise indentation test setup. They used a micro-manipulator, an MPC 200 model, which can move the catheter up and down with incredibly fine control, like 1 micrometer steps.
Oh.
As the micro-manipulator pushes the catheter tip down onto a surface, a commercial load cell, a very accurate Honeywell force sensor placed underneath, measures the actual applied force independently.
So they can compare the sensor's reading to a known accurate force measurement.
Exactly, and they did it very carefully. Lower the tip 1 micron, wait 30 seconds for everything to stabilize. Take 15 readings from each piece or resistor on the sensor and average them. Repeat for the next step.
Painstaking work.
Very meticulous. And it was all automated using LabVIEW UW software, controlling the equipment, acquiring the data, ensuring consistency across hundreds of measurements.
And this incredibly detailed testing wasn't just to prove the sensor worked, right? It feeds back into the haptic system.
Precisely. This characterization allowed them to define those crucial force ranges for the haptic feedback, linking specific vibration patterns to clinically meaningful thresholds.
Right, the low, normal, and high force ranges.
Exactly. Low force, 0 to 0.15 newtons. They linked this to that higher risk of arrhythmia recurrence. So the haptic signal for this range essentially tells the surgeon you're likely not applying enough force for an effective lesion.
Okay, then normal force, 0.15 to 0.35 newtons.
That's the target zone, the safe ablation range, the haptics here signal. You're in the sweet spot for good lesion formation with low risk. This is where the surgeon aims to be.
And high force.
Yeah.
Anything above 0.35 newtons.
This triggers a warning vibration. It signals increasing risk, potential tissue folding, maybe ineffective ablation, and at higher levels, that dangerous risk of perforation, like the 0.77 N seen in the pig heart tests.
So the testing directly translates raw force numbers into clear, actionable warnings and confirmations for the surgeon, delivered right to their hand.
That's the core idea. Bridging the gap between the physics and the clinical reality, making the feedback intuitive and directly relevant to patient safety and procedural success.
Okay, so we've got the design, the packaging, the meticulous calibration. Now for the ultimate test.
Yeah.
Putting it to work in a biological setting. You mentioned porcine heart tissues.
Yes, the crucial validation step. They indented the catheter tip onto dissected porcine heart tissues, specifically samples from the right ventricle, RV, and the left ventricle, LV. This is much closer to the real clinical environment than just testing on a hard surface.
And how did the sensor itself perform during those initial characterization tests before the tissue? The numbers look good.
They did. The piece resistors showed that nice linear response above 0.02 newtons. The average normalized sensitivity was high, around 0.022 per newton, with a really strong linearity indicated by that R-square value over 0.985.
So very consistent.
Very consistent. They noted that slight bit of nonlinearity right at the very beginning, below 0.02 N, possibly due to initial contact mechanics or friction, but overall, very reliable. The calculated uncertainty was also very low, about 0.022 newtons, expanded uncertainty giving confidence in its precision.
Okay, solid baseline. But tissues are different, right? Squishy, non-uniform. What happened when they actually indented the porcine heart tissue?
You're right, biological tissues add complexity. And they did observe something interesting. The change in resistance measured by the sensor when pushing on the heart tissue was generally less than what the calibrated load cell underneath the tissue measured for the same indentation depth.
Less. Why would that be?
It likely comes down to the tissue itself. It's compliant, it's soft, it's not perfectly uniform like a rigid test block. So the tissue itself probably absorbs or distributes some of the applied force. Think of it like pushing on a firm mattress versus a block of wood. The force felt by the sensor embedded in the tip might differ from the total force registered by the scale underneath the mattress, because the mattress itself deforms and absorbs energy.
Okay, that makes sense. The tissue acts like a buffer. Did the sensor still behave predictably, though?
Yes, and this is the crucial part. Even though the absolute reading might differ slightly due to tissue compliance, the response from the piezoresistors within the sensor was still linear and consistent as the force increased. It reliably tracked the changes in force applied to the tissue. They also saw, again, some differences in sensitivity between the different bridges on the sensor during tissue tests. Bridge 2, for instance, sometimes showed a lower response.
So not a sensor flaw, but information.
Exactly. It reflects the reality of pushing on non-uniform biological tissue. The force isn't perfectly distributed across the catheter tip. The sensor was actually detecting this unevenness, which is valuable information in itself about the tissue interaction. It confirms the sensor can pick up these subtle variations.
Okay, so the sensor works even on squishy real-world tissue. How did the haptic feedback system translate all that during the tissue tests? Could the surgeon feel the difference?
Yes, the haptic feedback performed really well in translating these dynamics. They monitored the signals going to the haptic motors using an oscilloscope and saw clear, distinct patterns corresponding to the forces. A key observation was the pulse width of the vibration signal, basically how long each vibration pulse lasted. When applying high normal force on the tissue, the pulse width was longer, creating a stronger, more intense feeling vibration. As the force decreased to medium or low levels, the pulse width got shorter, making the vibration feel different, less intense.
So you could feel the force level changing.
Qualitatively, yes. And those transition clicks they programmed were clearly activated. Indenting to around 0.1 N on the load cell triggered transition click 3, the signal for low normal force. Pushing harder to 0.25 N activated transition click 2, the medium normal force signal. And when they indented directly onto the RV tissue, primarily applying normal force, they observed that motor 1 vibrated as expected when the sensor bridges showed similar sensitivity readings. If the force became more angular, indicated by differing bridge sensitivities, motor 2 would likely have become involved.
So it successfully provided that intuitive real-time feedback based on the force applied to the actual heart tissue. It told the operator not just that they were touching, but how hard and potentially how.
Precisely. It demonstrated the system's ability to close that loop in a relevant biological context, translating the complex sensor data into understandable tactile cues.
So as we wrap up this deep dive, it really feels like we've covered a significant leap forward. This isn't just one component, it's a whole integrated system. We've looked at this MEMS-based force sensor, the vibrohaptic feedback, the really clever packaging with the FTS and those pogo pins. It's a complete solution. And the results look strong, high sensitivity, demonstrated ability to discriminate forces, and validation on actual heart tissue. Quite an achievement.
It truly is, and the implications are potentially huge. Giving surgeons back that sense of touch in MIS, it's fundamental. It could lead directly to safer procedures, fewer complications, more effective treatments. Think about reducing arrhythmia recurrence after ablation, minimizing accidental tissue damage. It empowers surgeons with a level of feedback and confidence that's often missing in current MIS procedures. It bridges that critical gap between sight and feel.
And the researchers aren't done, are they? What's next?
No, they're looking ahead. The paper mentions their plan is to move towards experiments on a larger scale, using ex vivo human heart tissues. That's the next logical step towards potential clinical translation, testing it in the most relevant model possible before considering in human trials.
Exciting times ahead for this technology then. So for you, our listener, here's something to think about as we finish. We're moving towards a future with more automation, more robotics, maybe even more remote surgery. In that future, how vital will technologies like this be? Technologies that redefine human dexterity, that restore or even enhance the surgeon's fundamental feel for the delicate work of healing. What new possibilities open up when surgeons can truly intuitively touch what they cannot directly see? It seems the future of surgery might just have a much better feel for the patient. That's got to be a good thing.